Ionization energy. In order to promote an electron in an atom from one energy level to the next energy level, some energy must be supplied. If enough energy is available, the electron can be removed and a cation with unipositive I positive charges formed. The amount of energy needed to remove the least tightly bounded electron from a 1 mole of gaseous atom is called the ionization energy. This process can be represented as ionization energy is measured conventionally in kilojoule per mole. It is possible to remove more than one electron from some of the atom. In case, the process can be represented as m gas equal to m positive plus 1 electron even. M positive turn into M2 positive plus electron E2. M2 positive convert into M3 positive plus electron E3, where even E2, E3 are the amount of energy that are needed to pull out the electron one by one, and are known as first, second, third ionization energy respectively. The ionization energy depend upon several factors which are given below. Size of an atom, charge on nucleus, screening effect of an inner electron, penetration effect of the electrons. Let us discuss these in order to appreciate fully the concept of ionization energy. Size of the atom. The ionization size depend upon the attractive force which the outermost electron is held by the nucleus. This is then depend upon the size of an atom because the attractive force between the outermost electron and the nucleus is inversely proportional to the distance present between them. Thus, in a small atom, the electrons are tightly held, where in a larger atom, the electrons are less strongly held. Thus, the ionization energy decreases as the size of the atom increases. Nuclear charge. With the increase in nuclear charge, the force of attraction between the nucleus and the outermost electron increases. Therefore, more energy is required to remove than outermost electron. As a result, the ionization energy increases with the increase in nuclear charge. Scoring effect. In atom with more than one electron, each electron repel every other electrons and is also repelled by every other electron. The attractive force that each electron feels from the nucleus affected by all other electrons in an atom. In addition, the inner electrons screen or shield the outermost electron from the positive charge of a nucleus. As a result, the effective nuclear charge, that is the charge actually felt by the outermost electron, is less than the actual nuclear charge. Therefore, the ionization energy will decreases. These thus increase in a number of electrons with decrease in the ionization energy. The penetration power of an electron. In case of multi-electron system, the electron in the s orbital penetrate to the nucleus more than the p orbital. It means that s electron experience more attractive force of the nucleus than p electron of the same shell. As a result, s electron are more tightly held by the nucleus than the p electron. Thus, the ionization energy of an atom possessing s electron will be more than those of the p orbital of the same shell. The valence value of the first ionization energy depend upon the combination of effective nuclear charge, atomic radii, and electronic configuration. It is important to note that elements with the lowest electronic ionization enthalpy are in the lower left corner of the periodic table. Element with low ionization energy loses electron relatively easily and form cation. They are called the reactive metals. A careful inspection reveals that the element with the high ionization energy are in the upper right corner of the periodic table. They are the non-metals. Electron with a high ionization energy do not lose electron easily. The variation of first ionization energy of an electron as a function of atomic number. It is clearly that the ionization energy are periodic function of the atomic number. The element of group 18, the noble gases, have the highest first ionization energy of the group and stand at the peak of the plot. Helium, the noble gases with the smallest atomic radius, has the highest first ionization energy of all the elements. It is the highly ionization energy of the noble gases that suggests the extraordinary stable electronic configuration of these gases. Let us now turn to the row in the plot where the ionization energy are the lowest. The elements are all member of group first. The outermost electron of lithium, sodium, potassium, rubidium, cesium are well electron. It is clearly that from graph that single s electron require relatively little energy for removal of the radius. Removal of outermost electron combined with needed to remove the electron. Cesium have the largest atomic radii as the lowest first ionization energy. This is because s orbital are in a new shell further the nucleus than electron in a producing noble gases helium, krypton, xenon. It is important to note that the shape of the p plot illustrates clearly that the periodic repetition of electron structure that occur on the predictable trend of ionization energy across period. It is observed that first ionization energy increases when we move across a period in a predictable from left to right. This is because each successive atom has one more proton in a nucleus. Thus, the positive charge on the nucleus increases steadily. But the attraction of the nucleus for the outer electron, the electron outer electron does do not change steadily. For example, in period third, the electron successfully added to the same outer electron since electron in a same cell do not shield each other very well from the attraction of the nucleus charge. The effective nuclear charge experienced by the outermost electron in each successive elements increase. As a result, the outermost electron experience a great attractive force for the nucleus. This results in the decreased atomic radius as the outermost electron are strongly pulled toward the nucleus as one move from sodium Z is equal to 11 to argon Z is equal to 18. The ionization energy increase significantly from sodium to argon. Although there is a general increase in the value of the first ionization potential across a period, the number of irregularity occur. For example, the first ionization energy of boron is lower than the first ionization energy of beryllium. The first ionization energy of oxygen is lower than the first ionization energy of nitrogen. It is important to note that the electron that is removed from boron is in the 2p orbital, where the electron that is removed from beryllium is in the 2s orbital, because in 2p orbital of the higher energy than a 2s orbital, an electron is more easily removed from boron than of from beryllium. In an oxygen atom have two electron in one of the 2p orbital. The pairing of two electron increases the repulsion between electron and thus cause oxygen to have lower first ionization energy than nitrogen. Trend of ionization energy across group. In general, the first ionization energy decreases in a regular way on descending the main group. That is because the element in a group have the same outer electronic configuration but with a different principal quantum number. As principal quantum number increases, the average distance of the electron in a shell from the nucleus also increases. Because the outer electron are further from the nuclear charge of the nucleus, they are less tightly held with the nucleus, and this account for a lower energy as one move from top to bottom of the group. A departure from the regular trend occur in a group 13, where the expected decreases occur from boron to aluminium. However, the value for the remaining element gallium, indium, thallium do not continue this trend. This is because the gallium atom is preceding by 10 element of the first transition element. This make the atomic radius of gallium much smaller than expected otherwise. As a result, the outer electron are tightly held by the nucleus and cause the ionization potential to increase. A similar effect is observed with the introduction of the second and third transition series before indium and thallium. This account for the increased ionization potential of indium and thallium are shown for group 13 elements. Just as S electron penetrate closer to the nucleus than p electron in p orbital penetrate closer to the nucleus than the electron in d orbital. The p electron feel the attractive force of nucleus more than d orbital. Thus, the energy of p orbital is lower than that of the d orbital of the same shell. Similarly, the electron in d orbital penetrated closer to the nucleus than electron in f orbital. The d electron feel the attractive force of the nucleus more than f orbital of the same shell. Thus, for the same cell, the ionization energy will be more to remove s electron than to the remove p electron, and p electron will be more than d electron, which in turn will be more than f electron. All these factor discussion above are interrelated. Thus, in a small atom, the electron are very tightly held, whereas in case of large atom, the electron are less strongly held. Thus, the ionization energy decreases as the size of an atom increases. This can be easily appreciated by the element of group first and group 2 of the predictable along with the element of main group. Group 13 to group 18. Successive ionization energy. All atoms other than hydrogen have more than one electron. The energy needed to remove the second most loosely bonded electron from a 1 mole of gaseous cation is known to the second ionization energy. A positive plus second ionization energy is equal to A2 positive plus electron. Because of the positive charge, the cation A positive attract electrons more strongly than the neutral atom A. It does. There is one electron less in cation compared to that in the atom of the element. As a result, electron repulsion reduces. It means more energy is required to remove the second electron than that of the first. Therefore, the second ionization energy is always larger than the first ionization energy. Similar, the energy required to remove the third most loosely bounded electron is called the third ionization energy. The larger the positive charge on a cation, the stronger is the attraction between the cation and the electron being removed. In addition, electron repulsion are also increases. The larger the positive charge on a cation, the more is the energy required to remove the electron. Thus, for any element, the value of the third ionization is always greater than the value of the second ionization energy. Similar, the fourth ionization that is greater than the third ionization energy, and so on. The successive ionization energy even to E8 of the first 13 element. Ionization energy to the right of the stepwise line involve removal of electron from the core of an atom. It is important to know that for each atom there is a large increase in ionization energy after all the outer electrons have been removed. For example, in case of the sodium, the first ionization value is 496 kilojoule per mole, and the second ionization energy is 456 kilojoule per mole. For magnesium, the first ionization energy is 737 kilojoule per mole, while the second ionization energy is 1447 kilojoule per mole. However, the third ionization value is 7738 kilojoule per mole, which is over 5 times as much as the second ionization energy value. After all the electrons in the outermost shell have been removed, the next electron must be removed from next to outermost shell, that is, it must be removed from the core. The core has a noble gas electron configuration. In the core, all the subshell that contain electron are filled. Increasing value of successive ionization energy spotted the idea that outer electron outside the noble gas core are involved in a chemical change. Inner electron in a core are too tightly bounded to the nucleus. Ionization energy provides strong evidence for the existence of the electron shell in an atom. Let us take an example of this sodium and remove all the 11 electrons from sodium. One can easily see that is a significant increase in energy needed between removing the first and second electron. There is another large increase between removing the ninth and 10th electron. This observing suggests that the increase occur when an electron being removed has to come from a new shell closer to the attractive charge of the nucleus. The difference between the energy level is so large that the logarithm to the successive ionization energy are plotted instead of the successive ionization energy themselves. One can easily interpret the pattern that the outermost n is equal to 3 shell of the sodium contain 1 electron. N is equal to 2 shell has an 8 electrons, leaving the 2 electron in the innermost n is equal to 1 shell. It is the large difference in ionization energy between outer and core electron that is responsible for only one kind of cation in group first and group second. Atom of transition element have d electrons of the n-1 shell as well as s electron of n shell outer side the core. The energy of an electron in an n-1 d orbital is not very different from the energy of electron in an ns orbital. As a result, atom of transition element often form more than one kind of cation. For example, iron form Fe2 positive and Fe3 positive. Measurement of ionization energy value. Ionization energy are measured by spectroscopic technique or in discharge tube containing the gas or vapor of an atom under consideration at low pressure. It is connected to the source of current. On increasing the potential difference, a stage reach when the sudden flow of current occur at the certain applied potential. This is a stage where the gas is ionized or the first ionization potential occur. If we increase the voltage further, there may a stage again where there is a after rise of the current. This gives the second ionization energy. In this way, we can calculate the successively ionization energy value, say third, fourth, fifth, etc. Ionization energy. In case of hydrogen, the first ionization value corresponding to 13.598 electron volt per atom. Thus, the ionization energy of hydrogen atom is 13.598 electron volt per atom. In SI, it is expressed in kilojoule. 1 electron volt is equal to 1.602 into 10 minus 19 multiply 6.023 into 10 23 kilojoule per mole is equal to 96.48 kilojoule per mole. 13.598 electron volt per atom is equal to 13.598 multiplied 96.48 kilojoule per mole is equal to 1312 kilojoule per mole. Thus, first ionization energy of an hydrogen is 1312 kilojoule per mole. Similarly, the first ionization energy of sodium have been evaluated to be the 496 kilojoule per mole.